Hello and welcome to the session. I'm Dr. Akshay Kumar from School of Computer and Information Sciences, IGNOU, and today I'll be discussing with you about a topic called strongly connected components of a graph. So, how we will proceed? First, we will define what are strongly connected components. Then we will try to discuss about where exactly strongly connected components can be used, and then we will be discussing about how to find strongly connected component in a graph. Basically, we need to discuss the algorithm in that particular case. So, what are strongly connected components of a graph? Well, most of the time, strongly connected components are defined in the context of a directed graph. So, a directed graph with the path from vertex Vi and Vj as well as path from Vj to Vi for all pairs of I and j, they form the strongly connected component. What does it mean? That in any graph, there has to be a link from any node. A path may not be the link, but there has to be a path from Vi to node Vj. I is one particular node and Vj is another particular node. Okay. Now, if there is such path, then from j also there has to be a path till I. So, that is how we define the strongly connected component. Okay. So, if we can formally define it, strongly connected components of a directed graph G with a set of vertices and set of edges are defined as a maximal set of vertices, right? So, we are looking forward to a maximal set of vertices, let us call that M, say, such that M is a subset of the set of vertices, okay? So, M is a subset of set of vertices with the constraint that any two pairs of the vertices in M, okay, say Vi and Vj are mutually reachable from each other. So, there is a path from Vi to Vj, as well there is a path from Vj to Vi, and both have to exist together. Okay. Together in the sense that within that particular graph. So, in other words, there is a path from Vi to Vj and from Vj to Vi. That is what is the basic definition if we have to talk about strongly connected component. How should we explain this better? Well, look into the example. Okay. So, here is a graph. Okay. This is a directed graph. You can see there are all the edges are directed edges. So, there is an edge from A to B as well as an edge from B to A also, right. Then there is an edge from B to C, then C to D and back to C, and there is a so. So, what you can see, this AB pair, right. So, since there is a clear cut path from A to B, which is a direct path, all right, as well as there is a path from B to A. However, if we look at B to C, there is a path from B to C, but there is no path back from C to B, right. So, there is a portion or somehow this particular portion is moving in only one direction. Okay. So, this is the first strongly connected component. AB forms the first strongly connected component. Similarly, C to D and D to C, we have path from C to D as well as from D to C. So, CD forms the second this strongly connected components, all right. And the third, this particular portion where we have x to y, y to z and z to x. So, there is a, if I want to move from x to y, there is a path. If I want to move from x to z, there is a path, right? Z to x, there is a path. What about z to y? Well, we have z to x and x to y, so there exists a path, right? What about x to z? There is a path from x to y and y to z. So that's how x to y and y to z makes a path. Therefore, all these components, x to y, there is a path, as well as y to x is through z. So, y to x you get y to z followed by x. So, there is a path from y to x also, though it is through z. So, these are also strongly connected component. Why? Because if x to y is there, there is a path from y to x, although it is from z. Similarly, there is a path from x to z through y and z to x, and from y to z, okay, and once again from z to y. So, these are all, so this is the third set of strongly connected component, maximal set of vertices. So, this is one maximal set of vertices, this is another maximal set of vertices, this is another maximal set of vertices. So, there are three basically subsets, okay, or three strongly connected components in the graph, the one which we have seen in the example. So, AB, CD and XYZ, as we were discussing. This is AB, this is CD and this is XYZ. They all these three forms the strongly connected components. Now, why do we need to discuss about strongly connected components about a graph? Now, first of all, it is a very typical application of depth first search and its use in a graph. That's all right, okay? But let's look into the application. There are many applications which are designed to run on strongly connected components separately. Why? The reason is, suppose you are trying to do some town planning, all right, and you know in the morning there are traffic snarls. You would like to know the components which are not strongly connected components, because they are maybe the components which may be the bottlenecks. Okay, so strongly connected components might be having bottlenecks in the form of when there is a directed link only. All right, so you need to do that particular analysis. Another very good example for this particular situation is World Wide Web. Right, now a World Wide Web can be represented using a graph and page rank computation algorithm, which is one of the most important algorithm, okay, by Google, may check strongly connected components. So, in this particular graph, look forward to, I mean, it may be using strongly connected component in determining many things together, because it is not a strongly connected component. So, from one set of strongly connected component, you have moved to, remember, World Wide Web is a directed graph, right? Because any link, that is HTML link or what we say hypertext link, moves you to a particular next node only. It doesn't bring you back. Okay, so that is a directed graph, and once you have moved out, and suppose there is only way out of that particular link, is there any way into a particular web page? Okay, now that has very important connotation as far as page rank algorithm is concerned. So, you may study page rank algorithm maybe when you are doing the course in data science. It is very, very important for you to know about. Okay, so in any case, the important thing is strongly connected components are to be determined in a graph in order to do or in order to perform several computations. Okay, so let us look into the algorithm then, right? So, what is the algorithm for finding the strongly connected components? Well, the algorithm to find strongly connected components is basically a four-step process only, and it revolves around DFS. Okay, so what it says is perform depth first search. Okay, on the directed graph G and number the vertices in the order they are visited. and the DFS call, once it got completed, that also is numbered for the vertex. Okay. So, you number the vertices in the order they are visited and when DFS call got completed for that vertex. And let us call it DFS completion time. Find the transpose of the original graph G. How to find the transpose of the original graph? Once you have find out the transpose of an original graph, then you perform the depth first search on this transposed graph by performing the traversal in the decreasing order of DFS completion time. So, the DFS completion time which we have marked in the first step, all right. So, now we will be using that DFS completion time, okay, to identify which got found out last, okay, and the order is decreasing. So, we will be starting with the highest node, all right, with the node for which the DFS was completed at the end, all right. And the subtree formed by the DFS on GT creates the strongly connected components. So, as we do this particular activity, we will come across the final that is strongly connected components. I mean, let us first try to describe this particular algorithm in little bit more detail. Well, for finding strongly connected component of a graph G to V, so the first step was traversal scheme DFS, all right. During this process, the vertices are numbered in the order they are visited as well as when the DFS call of that node is completed. So, we will perform, as I am repeating this particular step, but we will be doing DFS, we will be numbering the vertices as we are visiting them, and on the return when the calls get completed, that is the time when we will be also putting a number at that point of time. Then comes the transpose. As I told you, we will know how to make the transpose. So, find the transpose of graph GVE by reversing all the edges of G. Remember, this is a directed graph. So, by reversing all the edges, what you are creating? You are creating a transpose of a directed graph. All right. So, basically you are just doing the transpose of edges in order to get the transpose of a graph. All right. So, what we are doing? Reverse the edge from U to V to V to U in the transpose graph. To compute the transpose of a directed graph, traverse the adjacency list representation of a graph. So, we might use the adjacency list representation, and within the adjacency list representation, we will be simply doing this particular activity. So, if for a node X, okay, or let us say node A, there is a link to B, right. Now, it will be transferred to, there is a from B to A, right. So, that is how this particular transpose is going to take place, but then you have to search the entire adjacency list. If there is an edge from a vertex U to V in the main graph, the vertex V will be in the adjacency list of vertex U. That is precisely what I was trying to say. Okay. And this process will be continued for all the vertices in the adjacency list. So, we will repeat this particular process and we are going to make the transpose of the graph. Now, a very important point to observe here is, it is to be observed that the graph G and its transpose GT have exactly the same strongly connected components. Why? Because after all, what is there? When strongly connected components are there, even if you are reversing the links, they are going to remain the strongly connected component. Why? Because there was a link from U to V and there was a link from V to U, right. So, even if you reverse all the links, those paths are going to remain. All right. So paths are going to remain. Maybe there was a direct link, now it has become a path. Okay. So that is something which you got to remember. It is very important when you are doing the or finding the strongly connected component, that observe that the graph G and its transpose GT have exactly the same strongly connected component, and that is what we will be using. Okay. So let's now further describe this particular algorithm. So now perform the DFS on the transposed graph, all right, in the decreasing order of DFS completion time in graph VE, okay, during graph G in fact. During this process, the DFS is performed from the highest value of DFS completion time, and mark the components not connected to each other. Okay. Once you get to mark these particular component, and then create a list of strongly connected components in that particular way. Any algorithm, if it has not been discussed with the help of an example, will lead us nowhere. So let us try to understand this particular algorithm with the help of an example. And the example is the same graph which we have shown in the very beginning with strongly connected components. So let's do so our step 1 of the algorithm was to do a DFS on the graph, numbering the vertices at the time of the visit. So if we start the algorithm from A, right? So A will be visited first. It is DFS algorithm. So we visit A1 first. After we have visited A, then we take this particular link and visit B. That is why visit B point is 2. Once we have visited B, since this particular link has already been covered, right, because A has already been visited, so we cannot revisit A. We will visit C only with the help of this particular link. So visiting C is 3, all right. Since we have visited C, DFS still goes on. We visit D, all right. Now we cannot, like C has already been visited, so the number over here is 4. Once we have visited D, next we can visit only X, so this is 5. From here there is only one link, it becomes the 6. Okay. Then we visit from Y to Z, it is 7. Now from Z, when we see there is just one link out and X has already been visited, all right. So X has already been visited, therefore the Z has nothing else to do, right. So it got completed, that is where we mark the completion time. So Z got completed at time 8, Y got completed at time 9, okay, because after you have visited Z, you reverse back to Y. We don't have any other link from Y. So once Z has been completed, Y is also completed. That's why its completion time is one more than that, 9. X, once again, there is no other link out from X. So we have visited Y. So next completion time is 10 for X. For D, once again, this is the same way, it is going to be 11. This has already been visited. Okay. So the completion time of C's call is 12. Then the B's call is 13. And finally, A, since there are no more edges from coming out of the A and no more vertices to be visited, so the completion time of A becomes 14, right. So we are able to mark the entire graph with the visit time, which was the first time listed over here, and the completion time of the DFS onto that particular node. This is the completion time of the algorithm or call for that particular node. right? So the A's call will get completed towards the end. That is how the recursive algorithms work, all right? So now we have marked this graph. Let us do the next step. Let's transpose. Okay, how to transpose? This is my graph. Now I want to transpose this particular graph. So how I am going to transpose this graph? As we discussed, reverse all the edges. Okay, so that means we'll cancel this direction of this over here. The direction of this will become this. All right, this direction will get cancelled. Now the direction is over here. Okay, link in and link out, so it's not going to matter much, but then we are just reversing the directions at every link. All right, this is also we are able to reverse the direction, and here we are able to reverse the direction. All right, so now everywhere we have reversed the direction of the link. This is a G transpose. All right. So now this becomes my G transpose or GT, okay, graph, the transpose of G. Why? Because we have reversed the links wherever they were required. All right. So we have got the GT next. Now what is the next step after the GT? Next step after obtaining the GT will be to perform the depth first search on GT. All right. So now if I want to perform the depth first search on GT, what was the constraint or what we had assumed? We will start from the highest numbered, okay, highest numbered completion time node. Which is that? A, right, because it got the highest number completion time. So we start from A, there is a link to B, all right. So my depth first search is going to be A, next is going to be B, but there is no link out from B, remember here, because this arrow has reversed, there is no link out. B is having just a link to A, all right, and A has already been visited. So what I have so the only possibility is that my depth first search has now given me two components A and B, which basically forms one of the strongly connected component. Now I restart my depth first search from the highest node, which is 12. All right. So when I restart my depth first search from 12, I visit C first, then I visit D. From there is a link to D, but there is no link out once again from D. And on this side, I cannot go because B has already been visited, right? So I mean, we have to go to D because B has already been visited. So we cannot go back to B. Okay. So from C, we can only move to D. Okay. So we move to 11. Okay. So from C, we move to D as far as my depth first traversal is concerned. Now what happens? D, the only way out is going to C. Okay. And C has been visited. Similarly, B has been visited, everything is visited. So my depth first search once again gives me another component CD. Okay? Okay. Next, I start once again with the highest numbered component, which is 10. D is already visited, so I cannot move into this direction. So from 10, I have only one link out, Z, so I visit X. Okay. From X, I visit Z. From Z, I visit Y through this particular link. Now from Y, I cannot visit X because it is already visited. Okay. So this terminates here. Z, we go back to Z. we cannot visit any other link. So, it terminates here, it terminates here. So, this is another component that is strongly connected component, that is X, Y and Z. So, this forms the third strongly connected component. So, if you remember the original diagram, this is exactly what we had marked. This is how we have marked our this thing, and these are the reversed links, okay, strongly connected components of this is GT, all right. These link may be slightly different to what we had earlier, but that does not matter. Like it is a reverse link, this is also a reverse link, this is also a reverse link. So, all the way we have all the transposed links over here. So, we got three components as we were discussing: AB, CD and XYZ in the depth first traversal of GT. And what was the order chosen? The order chosen was the completion time of the DFS in the original graph, that is G. All right. So, what are the acyclic components of this particular graph? So, if I can club these two as one component, this two as another component and these three as another component, right? From AB, there was a link out to this particular thing in the original graph, right? So, that is how from AB we have a link to CD, then from CD we have a link. So, this is my acyclic component as far as graph was concerned. This is basically each one of them. AB was strongly connected component, CD was also a strongly connected component and XYZ is also a strongly connected component. But how are they linked? From the original graph or from the original link you can ascertain AB to CD, right. So, CD basically this basically represents a set of vertices in this particular case, but this is how the linkages are and this is how the linkages were in the original graph. All right. Now, what is the time complexity of this algorithm? Okay. So, suppose G, which is the graph with a set of vertices and set of edges, is an undirected graph with V being the number of vertices and mod E is number of edges and represented through adjacency list. Then the sum of lengths of all adjacency lists is 2E. Right. In adjacency list, each edge is represented twice, but in this particular case, even this 2 may not be there, because why 2 is not going to be there? Because the 2 is not going to be there here, it is just the E only. This 2 was the case when we were dealing with undirected edges. These are directed edges. So, they will be represented only in one list. They will not be appearing in two lists. So, this 2 is incorrect. Okay. So, DFS visits each node only once in the adjacency list. Okay. Therefore, the time to complete visiting all edges and the associated vertexes of order of V plus E. Okay. Also, the time taken to create the transpose GT is order V plus C, because we are traversing all the lists and every edge once. Because it is a directed graph, therefore, edges are occurring only once. All right. So, the total time complexity is also order V plus E, this particular order for both the steps, right. So, this particular overall order is going to be order V plus E only. So, now let us try to summarize what we have discussed in this particular session. That strongly connected components are the maximal set of vertices of directed graph that are mutually reachable. The algorithm for finding strongly connected component use DFS algorithm. the algorithm performs DFS twice. First time on the graph and the second time on the transpose of the graph. With this, we end this particular session. I hope you must have understood the strongly connected components well. Thanks for being with us. Bye.